Hi everybody, we're going to do 3.4 today, rates of change. For our warm-up, we're going to use a problem here where we have to definitely use the quotient rule at first glance, but then if you notice, the numerator also includes a product rule. So this is a good way to start class today. So we need the rules f divided by g and f times g prime. So f divided by g prime, the quotient rule is f prime g minus f g prime divided by g squared, and f times g prime is f prime g minus plus f g prime. Okay, so setting up this problem to begin with, we are first going to set up the quotient rule, and then as we set up the quotient rule, that is when we come across our product rule. So I'm going to indicate in the first line of work what needs to be derived, and then I'll derive it in the second line of work. Okay, so now when I'm actually deriving, here's where I'm using my product rule. So e to the m derives and stays e to the m to the 1/3 stays, plus e to the m stays, m to the 1/3 derives to 1/3 m to the negative 2/3. M squared plus 3 stays, minus e to the m to the 1/3, 2m. Divide by m squared plus 3 quantity squared. And I realized that I did make a typo up here. I put a prime mark and it should have been a squared. Okay, in a problem like this, I would not bother to simplify. I would just leave your final answer as is. That's totally acceptable. Okay, and if you're worried, instructions on a quiz or test, I would give you the instructions to leave it as is. Okay, so far we've talked about the derivative as limit of a difference quotient and slope of a tangent line. Now we're going to start talking about it as the rate of change. So this brings us back to that 2.1 section that we started off with. Recall that the slope of a secant line represents the average rate of change, and the slope of the tangent line represents that instantaneous rate of change. So in 2.1, we needed to use the slope formula, and we were using increasingly smaller delta x's or delta t's to accomplish this, and that allowed us to at least estimate what an instantaneous rate of change would be. But now, in Chapter 3, an instantaneous rate of change is exactly equal to the derivative at that point, okay, which is equivalent to the limit as delta x approaches 0 of change in y over change in x, or the same thing that we were covering in 3.1, the limit as x1 approaches x0 of f of x1 minus f of x0 over x1 minus x0. Okay. All right, so find the rate of change of an area of a circle. So this is just kind of warming up to it. We can find the rate of change of any equation. Sometimes there will be some meaning to these equations. Sometimes they'll just be basic functions. Okay, so if we want the rate of change of a circle, well, we have to start with that area of a circle, which is pi r squared, and we would derive it with respect to r, with respect to the radius. We would notate this as dA over dr, or a prime, and this is just a power rule. Pi is a coefficient, so it becomes 2 pi r. Not a coincidence that this is a circumference formula for the circle. All right, surface area of a sphere with respect to radius. And the area of a sphere is 4 pi r squared. So dA over dr is equal to 8 pi r. Volume of a cube with respect to its side, s, when s is equal to 5. So volume equals side cubed, the rate of change, dv ds, 3s squared, and then more specifically, dv ds when s equals 5 would be 3 times 5 squared, which is 75. 75 volume units per side unit. These types of problems, these examples that are here, I'm just showing them to you now that you can derive with respect to any variables. Typically, we're going to take a look at the change of the area, for example, of a circle with respect to time later in this chapter. Those are going to be called related rates. Okay. More commonly, we're going to use the position function. So position function is usually represented with s of t, and it's talking about the distance from the origin at time t. So the derivative of the position function, which could be notated as ds over dt or s prime of t, is the velocity. How far have we gone over a certain time, right? Position over time is velocity, v of t. Instantaneous velocity is what we're really talking about here. Very important. Unlike speed, with velocity, the sign of it represents the direction. Right? When we're driving in our cars and we're using miles per hour speed, we're not saying we're ever going a negative speed. It's always a positive. But velocity, north and east are both positive directions, whereas south and west are both negative directions. So a truck enters the off-ramp of a highway at time t is equal to 0. Its position after t seconds is s of t equals 25t minus 0.3 t cubed meters. And this equation applies from 0 to 5 seconds. How fast is the truck going at the moment it enters the off-ramp? So with these types of problems, you're thinking about, well, what type of formula do I need in order to answer this question? So how fast? That's a velocity question. So we're going to take our equation and we're going to find the derivative. So s prime would be 25 minus 0.9 t squared. And then at the moment it enters the off-ramp, so that's when. That would be when t is equal to 0. So s prime of 0 equals 25 minus 0.9 times 0 squared, or 25. Our units here would be meters per second. Okay, Galileo's formula. So for those of you who have taken physics, or will be taking physics, you'll come across this, of course. Galileo's formula based on gravity. S of t is equal to the initial position, s of 0, plus initial velocity times time, minus 1/2 gt squared. G is gravity. Okay, now I have this white box. The textbook is going to show it to you as velocity equals initial velocity minus gt. I don't really like to show this because I don't want you to think of it as something that you're going to memorize. The velocity is always the derivative of position. Of course, it derives to this, but you don't have to think of it as another thing to memorize. Understand and memorize how the position is created, and then from there you can always derive and find the velocity. So acceleration due to gravity is always 9.8 meters per second, or 32 feet per second, depending on the unit that we're in. Notice that the 1/2 gt squared term is already negative. Therefore, the gravity getting inputted there is being inputted as a positive. So you might learn it as a plus 1/2 gt squared, and if that's the case, then of course gravity is negative. No matter what, gravity is certainly pushing us back down towards Earth. All right, so finding the maximum height. A stone is shot with a slingshot vertically upward with an initial velocity of 50 meters per second from an initial height of 10 meters. So the units are really important. And of course, our initial velocity and initial heights are important. So find the velocity at time t equals 2 and t equals 7 and explain the sign change. So the first thing you always want to do is come up with the equation, the position equation based on the information that is given. So S of t equals initial position, which is 10, plus initial velocity, which is 50, minus 1/2 the gravity, because we are in meters, we are using 9.8 t squared. Okay. The next thing you can come up with is the velocity equation, right, which is the derivative of position. So the 10 goes to 0, the 50t goes to 50, and the 1/2 gt squared becomes gt. So 9.8 minus 9.8 t. They want to know what's the velocity at 2 and what's the velocity at 7. So we're using our velocity and we're inputting in those values. 50 minus 9.8 times 2 will give us 30.4 meters per second. And 50 minus 9.8 times 7 will give us negative 18.6 meters per second. So why did we have this change in sign? Right? Positive, negative tells us direction. So at 2 seconds, we are still heading upward, right? That slingshot shot vertically upward. So we are still on the incline. And then at 7 seconds, we are now falling back down towards Earth. So shooting up versus falling down. What is the stone's maximum height, and when does it reach the height? So you can think about this from an Algebra 2 perspective. This question was certainly embedded in Algebra 2, but we're going to think about it from the calculus perspective. Okay? And just as a reminder, the axis of symmetry in Algebra 2 from standard form was opposite of b over 2a. See if you can figure out where that connection comes in. So what is the stone's maximum height, and when does it reach that height? How do we think about that? Right, this is a parabola. That's not totally accurate. It starts at 10, it shoots upward, and it comes back downward. Okay, the max height, right, is right here. It's the vertex of the parabola. But I don't want to think about it from Algebra 2. I want to think about it from calculus. So what's happening when we're at that maximum height? Right? We shoot this slingshot. We shoot the object upward. Gravity's pushing it down. Eventually it gets that max height and it starts coming back down to Earth. So at that moment, at that instant that we are at that max height, gravity has completely stopped our initial velocity. Our velocity right here is 0. V of t is always going to equal 0 at these turning points. So if we know that the velocity is 0, and we know the velocity equation equals 50 minus 9.8 t, then we can solve for t. And t comes out to be 5.1 seconds. So as you're solving that 50 minus 9.8 t, that is exactly where the opposite of b over 2a comes from our original position equation, right? The position equation is our parabola. All right, so now we know when it reaches the max height. What is the max height? We need the y coordinate, so we need a position. So we need s of 5.1. So 10 plus 50 times 5.1 minus a half, 9.8, 5.1 squared. And that comes out to be 137.5 meters. Okay, last example for today. What initial velocity is required for a bullet fired vertically from ground level to reach a max height of 2 kilometers? We're going to change the 2 kilometers right away to 2,000 meters. So what initial velocity is our question here? It's fired vertically, ground level. Okay, so the first thing that I start to fill out is, I've highlighted my givens, I've circled my givens, so I don't have to write that, but my position function, right? So I know that it's S of t equals 0 because it's ground level. I don't know my initial velocity, so I'll leave that in as another variable. 1/2, I'm using meters, so 9.8 t squared. So I filled in what I know. Okay. I also can do a little bit of work. I can come up with my velocity equation based on what I have here. V initial minus 9.8 t. Okay. So what initial velocity is required for a bullet to reach a max height of 2,000? So we know that our max height is 2,000 meters, right? We know that happens at the vertex. And therefore, we know that that can help us solve and essentially figure out our initial velocity. So one thing that we can do, right, is figure out when does it reach this max height. Okay. We're going to have to use a system of equations, though, in order to, remove some variables somewhere, right? Right now our position function has 2 variables. Our velocity function also has 2 variables, but if we put these together, maybe we can come up with one equation with 1 variable. So I'm going to take my velocity and manipulate it a little bit, right? Again, I know my max height. I know that max height occurs when velocity is 0. So therefore, the relationship is at the max height only, right? Then my initial velocity is equal to 9.8 times t. So then I can take that idea and substitute it into my position, along with the 2,000 meters. So this scenario is happening at this moment only. So 2,000 equals 9.8 t minus 1/2 times 9.8 t squared. So 2,000, oops, I missed a variable here. Let me go back. The 9.8 t goes in for the v sub 0. There's still another t attached to it, and that's what I forgot to write. And then minus 1/2 9.8 t squared. Okay. So now this is important because I only have t squared terms on the right-hand side. I don't have any t terms. So I can very easily simplify this and solve for t. If I divide by 4.9 and I square root, t is equal to plus or minus, but we only want the positive, 20.2 seconds. Okay, so the question is asking what initial velocity do we need? So now we can take that time and put it into the relationship we have for initial velocity. So v sub 0 equals 9.8 multiplied by 20.2. Therefore, that comes out to be 198 meters per second. So this was a tough one because it took a lot of a lot of work analyzing and interpreting what the question was asking and what the given information was. All right, but that's it for 3.4. We will go over the problem set in class.